Friends, welcome to the next lecture on spring and mass system. It's a very important topic, and spring is one of the most important element in mechanical systems. It absorbs energy and dissipates very slow. As an automobile lover, you would have seen an element in your shock absorber is spring. The spring can be of multiple types. For example, it can be a helical spring. It can be a leaf spring, which is used in buses. Earlier, leaf spring used to be made out of metal. Today, it is made out of elastomers. Right? In your typical ballpoint pen, again you can see a spring which is put in the front end of the system. So, spring is very important element. In this lecture, we will try to cover the basic concepts. We will try to have damped spring mass systems, then forced vibration, nonlinear spring mass system, design consideration for a spring mass system, a case study, and then finally, you will try to have a recap. Today, when we construct tall structured buildings or a tall statue, we always have to make sure that it withstands the natural disaster. It can be wind, it can be rain, it can be an earthquake. So, in order to balance the weight, again they try to use a spring mass system. What is a spring mass system? A spring mass system is a fundamental mechanical model consisting of a mass attached to a spring that can compress or extend. When you are trying to travel in a bike, you are sitting, so that's a mass. So, when there is a brake applied or when there is an undulation or a pothole, the spring is compressed and then it is relaxed by this C. So, here the mass compresses the spring, where K is the stiffness of the spring. You can use the mass also in the downward fashion, where it is used in spring balance. For example, to measure weight 0 to 5 kgs, 0 to 15 kgs, you can also have 0 to 50 kgs. More the weight, lesser will be the resolution. So, you can have a spring attached to a mass. Now, here what will happen is you will try to see a graduation. Based on the graduation, you can try to figure out what is the kgs weight. So, how do they do it? They have a linear scale where in which the graduations are there. So, there will be a floating reader. So, it says 5 kg. So, now we would have already calibrated with respect to display kg versus displacement. This displacement in turn is attached to the spring stiffness K. Okay. So, you will try to have something like this. So, we will always work in the linear portion. So, you can even go to sabji mandi, vegetable vending, and then you can try to buy. When you go to buy cloth in kgs, for example, for waist cloth, again you will see a spring balance. So, spring balance, here what happens, the weight is attached and then the spring elongates. So, here it is tensile, here it is compression. This simple setup is widely used to analyze and understand various physical phenomena including oscillations and vibrations. You can also put the spring on top of a table and try to see how much does it vibrate. For example, that's how they try to do on a speedy train. On a high-speed train, they used to put a dial gauge and then they used to measure the deflection and say what is the vibration it creates when the train is going at very high speeds and when the brakes are applied. The components of a spring mass system. It has M, it has K, and it also has a damping element. What is M? M represents an object with a certain amount of inertia. The mass resists change in its state of motion when the force is applied or forces are applied. So, here X is the deflection. Spring, an elastic element that exerts a restoring force when deformation happens. So, that is called as the spring or it is called as the spring stiffness. Third element is going to be the damping element. Damping element, it dissipates energy, reduces oscillation or it dissipates energy by reducing oscillation over time and is crucial in controlling the system's stability and response to external disturbance. Okay. Damping is very, very important because once the spring is taking a load, right, then the spring has to dissipate the energy such that it can bring the mass back to the original position. Behavior of spring mass system. When the mass is displaced from its equilibrium position and released, it oscillates back and forth due to the restoring force of the spring, that is the spring stiffness. You take a weight, you apply to a spring, you pull the weight and release it. It starts vibrating or it starts oscillating. Right? It oscillates back and forth. Why are we saying back and forth? There will be a mean, it can go up and down. The displacement can be same or it can be more. So, assuming that this is positive and this is negative, this is the mean position. So, it will go back and forth, back and forth. Initially, it will be both sides uniform and over a period of time, it slowly dies down. The system exhibits simple harmonic motion if no damping or external forces are present. It will keep on be vibrating. So, now there are two things which come into existence. So, what are the two things? What are the key characteristics of this motion? They include amplitude and time. For example, if you try to take amplitude and time, so it might go like this. Right? So, the key characteristics of this motion, simple harmonic motion, includes amplitude, the maximum displacement from the mean position or equilibrium. Second thing is, what is the time period it takes to complete one cycle. So, one cycle starts from here and it goes up, it comes down and then it goes up. So, this becomes your one cycle, T. Time taken to complete one full oscillation or cycle. So, generally T is represented as 2 pi root of mass divided by K. So, moment you know T, from there we try to derive frequency. Frequency is the number of oscillations per unit time, F. Every mass or every spring or every object will have its own natural frequency. The frequency at which the system naturally oscillates without any force is called as natural frequency. We always try to play around this natural frequency. For example, if there is a natural frequency for a given element, so the vibration we always make sure it does not go close towards the natural frequency. If it goes close, then there will be a major disaster happening. So, frequency of oscillation will be maintained very low compared to the natural frequency of the given object. So, then how will you change the natural frequency? So, the frequency can be changed by changing the stiffness. Stiffness can be changed. How will you change the stiffness? The material can be changed or the design can be changed. So, based on that, to some extent the stiffness can be changed. Predominantly we go around changing the material. So, what are the practical applications of spring mass system? So, one is vehicle suspension systems. It is very important. See, uses springs and dampers to absorb shocks from the road, providing comfort and stability for the passenger. So, here this is the mass of the car. So, here is the spring, here is the damping, and then here is the displacement. So, the car will move like this, right. So, then it is also used in the instrument which is called a seismology for seismic measurements, modeling buildings and structures to understand and mitigate the effect of earthquake. So, spring is attached to a mass, this is attached to a dashboard, and then you try to see the displacement of the mass with respect to a scale. Seismology is a study of seismic waves, and here we are now trying to build buildings, the shape of the building, the weight which is getting distributed on the building. We are trying to design keeping the effect of earthquake, or we are trying to mitigate with the earthquake. Next is mechanical clock and watches. Utilize a spring and masses to keep accurate time through controlled oscillation. So, here you see there will be lot of gears, there will be a coiled spring. This is a normal spring, you can also have a coil spring. So, in your scooter, this is normal helical spring and this is coiled spring. In your scooter, kick scooter, when you try to kick, it goes down and then it gets released very fast. They are all coiled springs. So, in a watch also we try to use a coil spring. So, the coil spring, when you try to give a key, it starts loading the coil spring, and coil spring slowly releases energy. Till it releases complete energy, the watch keeps on working. So, if you see olden wall clocks, where in which they used to have a key and give motion to the key, they basically load the spring. Then vibration oscillation systems, it protects sensitive equipments by absorbing and reducing unwanted vibrations. For example, if you buy any of the high resolution or a highly sensitive equipments, we always try to put a shock absorber. When you try to install a lathe machine, milling machine, or even your washing machine, your grinder, we always have a spacer between your object or your instrument product with respect to ground. So, in between what we put is, we always try to put a rubber pad or a spring attached thing. So, those are nothing but absorbers which reduces the unwanted vibration. Engineering and physics education serves as a foundation model for teaching concepts of dynamics, control systems and oscillation motion. There we use the spring mass system. Let us go back to the Hooke's law, what we studied when we studied about the uniaxial tensile testing. So, we studied F is equal to minus Kx, where F is the restoring force exerted by the spring when it is compressed or stretched. F is the force. I will just give you an exercise. You can try to remove your ball point pen and then you try to see a spring which is there. Then you try to go to your cycle stand, cycle support stand is there, no? Where you, when you park a cycle, you place it with a stand. So, there you see there is a spring. Both the springs are coiled or helical in nature, they are helical. Here also it will be helical in nature, right. But the two springs have different stiffness. Why is it so? It is basically the spring constant is different. A measure of the stiffness of the spring, a higher value indicates stiffer spring that requires more force to produce the same displacement. More the stiffness, more the force required. So, when you try ballpoint pen, maximum load maybe 2-3 kilos load it will have to take. When we try to use a cycle stand, it has to try to take a load of 15-20 kgs. That is what it is. So, x is nothing but the displacement. The distance the spring is compressed or stretched from its natural position is called as displacement, x. The negative sign which is there indicates that the force exerted by the spring is in the opposite direction of the displacement. So, F equal to minus Kx, this minus is what we are discussing. Minus the negative sign indicates that the force exerted by the spring is in the opposite direction of the displacement, meaning the spring tries to return to its equilibrium position. Newton's second law of motion, we have force equal to Newton's second law states that F equal to ma. So, this is an application to the spring mass system, where m is the mass and a is the acceleration. M, the mass of the object, is attached to the spring. A is the acceleration, the rate of change of velocity of the mass. In the context of spring mass system, Newton's second law can be applied to relate the force exerted by the spring to the motion of the mass. So, earlier we saw F equal to minus Kx, now we are seeing F is equal to ma. So, now I can equate ma equal to minus Kx. That is what is told here. So, the force exerted by the spring, Hooke's law, this is Newton's second law, and this is the, we are trying to take F and F, equate F and F here. So, derivation, start with the Newton's second law applied to the spring mass system, F equal to ma. Substitute the expression for the restoring force from Hooke's law, ma equal to minus Kx. Rearrange to form the equation of motion. This is very important. M double dot x plus Kx equal to 0. It is the second order differential equation describing the motion of the mass. So, we have just converted into a second order differential equation such that we can understand more about the motion of masses. So, derivation for natural frequency, the equation of motion can be solved to find the natural frequency of the system. Assuming a solution of the form x of t is equal to a cos omega suffix n t plus phi, differentiating twice with respect to time, we try to get a x double dot with respect to t is nothing but minus, please note down, minus omega n square a cos omega n t plus phi. So, now substituting this into the equation of motion, we get m, if you go back, m double dot x plus kx is equal to 0. So, m double dot x plus x, we substitute it here. Simplifying, to find the natural frequency is nothing but omega n is equal to root of k by m. So, if you go back, we had a similar equation prior. So, what did we see that? We saw the time period is 2 pi root of m by k. So, now here what we are trying to see is omega is root of k by m. Okay. So, this is the natural frequency. Why is natural frequency very important? Because once you know the natural frequency, the vibrations can be played. The natural frequency omega represents the frequency at which the system oscillates when displacement from its equilibrium position and then released, when no external forces or damping acts on it. It depends on the stiffness of the spring and the mass attached to it. So, if we want to play with the natural frequency, you will have to play with its mass and spring stiffness K, M and K. So, you can add mass, omega will change. You can add stiffness, omega will change. Stiffness is a material property. You can play with stiffness. M is the mass. So, when we add mass, again there comes a design. So, you can change the design, the topology optimization. There are so many new techniques which has come into existence. So, natural frequency is very important to be calculated. Moment you know the natural frequency, we will try to plan our system accordingly. So, in natural frequency, without any mass, the system starts vibrating. So, what is damping ratio? I said the energy gets dissipated and it almost the vibration attains 0. So, now when you talk about that, so there is something called as damping which happens, and when you look into the system, we also said that in the beginning damping element, right. So, this damping element, we will have this damping ratio. So, damping ratio zeta. Damping ratio denoted by Z or zeta is a dimensionless measurement. When I say ratio, it will be dimensionless measure that describes how oscillation in the system decay after a disturbance. You have a spoon, you have a maybe an orange here, and then you try to close this or hold it in your mouth. So, here there is a force which is getting applied. So, moment you apply a load like this, and then you pull it, it starts vibrating. This vibration does not continue for a longer time, it vibrates and then dies. So, that is what is the decay after a disturbance. It is a key parameter in the analysis of damping harmonic oscillators such as spring mass system, and is defined as a ratio of the actual damping in the system to the critical damping. So, here zeta can be represented is calculated from C divided by 2 root of Km. You see, spring stiffness and mass keeps on coming in multiple formulas when we talk about spring mass system. Okay. In terms of time, yes, it came. In terms of natural frequency omega, it came. When you talk about zeta, the damping ratio, again it comes. So, please be careful about the formulas. So, what is C? C is the damping coefficient which is represented in units like Newton S per meter. The spring constant is Newton per meter and the mass is always in kgs. So, interpretation of the damping ratio. So, what are all possible? Zeta can be less than 1, zeta can be equal to 0, zeta can be greater than 1. Okay. So, when zeta equal to 0, the system is called as undamped system. No damping is present and the system oscillates indefinitely at its natural frequency. Very important, please note, undamped system. When the system is underdamped, the system oscillates with a gradually decreasing amplitude. The oscillation decays over time, but the system still oscillates. When you say zeta equal to 1, it is critically damped systems. The system returns to equilibrium as quick as possible without oscillating. For example, you need to have this in cars. If when you hit a pothole, if there is an oscillation which is happening, it has to be arrested very fast. Maybe in one oscillation or in the second oscillation it should die. So, that is called as a critical damped oscillation. The system returns to the equilibrium as quick as possible without oscillating. This is the optimum level of dampening for systems where a fast return to equilibrium is desired, such as in automobile suspensions. When it is greater than 1, it is called as over damped. The system returns to equilibrium without oscillating, but slower than the critical damping case. So, the difference you should note down. In critical damp system, the system returns to equilibrium as quick as possible without oscillating. Here in over damping, the system returns to equilibrium without oscillating, but slower than the critical damp case. Okay. So, in both the case, when you go back to zeta, you see a spring stiffness and mass. So, the mass whatever you apply in the spring system, spring mass system. So, you had a spring, then you had a mass, right. So, this has to be damped. So, this is spring K, this is mass M, and this is mounted. So, importance of damping ratio. The damping ratio is crucial in understanding the behavior of a mechanical system, especially in the context of vibration and stability. If some object keeps on be vibrating, then it is going to bring lot of uncomfortable situation for the object or the system. Stability is very important. It helps engineers design systems to avoid excessive oscillation and ensures that components return to equilibrium in a controlled manner, reducing the risk of resonance and failure. Let us try to work on a very simple problem to understand the concept whatever we have gone through. Calculate the natural frequency of a spring mass system where mass is 5 kg and the spring constant K is 200 Newton meter. So, what is the formula for natural frequency? Is omega n equal to root of K by M. So, what is K? K is 200 by Newton meter. What is M? M is in 5 kg. So, substituting back omega n equal to root of 200 divided by 5 kg, which is root of 40 radians by second. So, omega n, the natural frequency is going to be 6.32 radians per second. So, now we will 6.32. Where is 6.32? 6.32 in our system is over damping system. So, the significance is understanding natural frequency is critical to ensure that operating conditions avoid resonance, which can lead to excessive vibration and potential failure. This is very important. So, you will have early failure because of resonance. Thank you very much.